All right, you guys are energized for the next session. So I'm really excited to introduce to you our visionary talk speaker, Dipti Vachani. She is the Senior Vice President and General Manager of the automotive business at ARM. Dipti leads the organization responsible for delivering ARM-based solutions in the transformational opportunities of automotive. Previously, Dipti served as Vice President and General Manager of the Product Management and Customer Enablement Division of the IoT Group at Intel. Before that, Dipti held several leadership positions at Texas Instruments and led the creation of the company's Sitara brand of ARM MPUs. Dipti is on the Women's Leadership Council for the Global Semiconductor Association. She holds a BS in Computer Engineering from Texas A&M, an executive MBA degree from the University of Texas, and is a graduate of the executive education programs at Stanford, Harvard, and Cambridge Business Schools. In her keynote, Dipti will discuss the holistic approach required to deliver the vehicles of the future and investments in hardware, software, and industry collaborations to make this vision a reality. Please join me in welcoming Dipti to the stage.
I have 2 kids in college. I have 2 girls. They're both in college. And I thought that I was free of Disneyland. And then I arrived last night going, oh my God, I can't do this. I can't do this anymore. I'm done. Maybe grandchildren. Maybe that's when I'm back again. Or the test conference, right? And so why am I at Disneyland again at the test conference? And I'll tell you, it's because if I see a vision for what we want to do in automotive and what we aspire to do in automotive, testability, verification, reliability, security, safety, that is going to be paramount. So the people in the room and the things and the topics you talk about are paramount to the success of this industry. We are moving faster than we ever have in the automotive space. And fast sometimes doesn't mean scrappy, doesn't always mean low testability, doesn't mean low reliability. We still have to do it at all the same standards that we've done in the past. We just got to do it faster. And so this collaboration between the topics that you guys talk about in this conference and the vision that the rest of us are trying to pull towards is going to be critical for our success in this space. So as you know, the automotive industry is going through the largest disruption that it ever has. I've been in this space for a very, very long time, and the speed at which innovation is happening, the speed at where it is required, and not only autonomous driving, but the experience we have in the vehicle, as well as electrification of the car, all of it's happening at the same time. And they're all, we often think about it as one. It's a fully electric autonomous car. Well, no, it's an electric car with more autonomous features and a more robust in-vehicle entertainment. Those are actually, from a technology standpoint, separate problems. And they're all being solved at the same time to give you one unique experience. And so, yes, the car is not the car that it used to be, and what we need for the future is going to be uniquely different. So what are those disruptions? I mentioned them already, but I want to tease this out a bit. What are those disruptions? There's electrification. Of course, we know what that means. The car is becoming more electric. There's automation. And often I get the question is, when are we going to have the first level 5 vehicle on the road? If I knew that answer to that question, I'd be somewhere else making a lot more money. We don't know. We don't know. It's going to be a while. But the point is, and what really matters, what we should all focus on, the point is more and more automation is going into the car every generation, and it needs to have the ability for future-proof. So that's what matters. That's what we read into that. More automation, ability to future-proof, and the race to more and increased automation is happening. And then the user experience. We want the iPhone experience in our car. We want to be able to do everything that we can do with our phone in our car, and we expect to have updated software, and we want updated features. And so what does that mean for the industry? What does that mean from what they have to do differently? Well, that means software-defined vehicles. That means that car has to have updated software in real time. And I mean, it's usually when it's parked at night, but imagine new software being downloaded as you're driving down the street. How does that work? Think about that just from a verification, testability standpoint. There's just new software being downloaded and it's real time while you're driving the car. The amount of stuff that has to happen to make that possible, as you and I all know, is actually very, very complex. There's a lot that has to go through that. So that's software-defined vehicle. Specialized compute. There's so much compute in these cars that compute has to be heterogeneous to the workloads that are being driven in the car, driven, no pun intended. The workloads being driven, downloaded onto the car. We got to make sure that compute has got the right components of acceleration versus general purpose compute. And so there's this level of what does that compute look like and what is that specialized compute? Safety and reliability. You all understand how critically important it is. We can't go faster, and if our iPhone heats up a little bit, then we just go back to the shop and get a new one. You know, it doesn't work that way in a car. It's so important for the safety of the human that safety and reliability are paramount in everything that we do. And artificial intelligence. The car is making decisions. Machines are writing software, and that inference is being downloaded onto the car. So, and if that isn't overwhelming right there, this is what the industry is trying to solve for all at once. That's what it takes. So, what is that doing? How are OEMs looking at this differently? First of all, they're re-architecting their cars. What was often many ECUs, working in isolation, different controllers, ECUs, electronic control units. Now they're looking at domain controllers. So they're looking at centralizing those computes so that they can have a controller that controls many different components of the car. Why is this new architecture make sense? Well, one, it makes the powertrain simpler because now we've got an electric car. Two, it makes software downloading simple. And three, it improves the ability to create autonomy within the car when you have several domains that you can control, right? Instead of having multiple ECUs independently working. And that translates into a central compute architecture. So what OEMs are looking at is, I have an IVI computer, that's an in-vehicle entertainment computer. I have a ADAS controller that's deciding, lane change, giving me warnings of the speed and things of that sort. Well, those are starting to merge because what is mapping technology in an IVI also could be used by the ADAS controller. So are they really just two separate controllers? Are they combined? And if I'm doing software downloads of artificial intelligence, doesn't it make sense just to have one central compute that it comes through? And so that's a central compute architecture. I'll talk a little bit more about that later. Cloud to vehicle connectivity, because you imagine software downloading and new software updates are going to require that kind of connectivity. And then I'm going to talk about chiplets. So why are we thinking about chiplets in the world of automotive? Because if you guys have thought about packaging and reliability, it's hard stuff at high temperatures when we start to break it up into chiplets. And we are going to solve that problem for automotive. And we are going to move to a world of chiplets in automotive. So where does ARM focus on this? What is ARM's place in this? First of all, how many of you here in the room have heard of ARM? Yes. You know what? If I had asked this question about maybe 2 years ago, it might have been less. What? Yeah, no, I don't. Well, yeah, that's true. 2 years ago, here maybe. It's really interesting what we do in the company as far as what we focus on. 60 to 70% of our R&D is spent on test and verification. And that usually surprises the public. You know what? I'm not surprising this room. I'm just going to walk off now. I'm done. You guys aren't surprised by that. But you know, I talk to the rest of the industry and they're like, what, 60 to 70% on test and verification, right? That's where your R&D is spent. Yes, that's how important this stuff is. We've got to make sure it works, and it just works right off the bat, right? That's so important. So we have a breadth of portfolio of ARM technology that we provide, and it's all done down to the low M class, all the way up into higher performance data center level IP that is automotive enhanced. That is, it has all the automotive hooks in place to enable certification ASLB and certification ASLD, and that's the automotive optimized. We also have a standard software framework where we allow for any ARM solution, if you use the standard framework, we allow for any ARM solution to have software interoperability. That's a big deal for these OEMs. And we have, obviously, with ARM, the largest ecosystem in the industry. And when we engage in the ecosystem, we look at solving the problem from three perspectives. There's three big buckets of things that we need to think about. One is the increase of software complexity. So the biggest problem is the amount of software that the OEMs are trying to solve for. It has been in the past silicon, and now the problem has moved to I've got so much software. My silicon just has to work. It just has to work because I need to focus in, and it has to be optimized, and it has to be specialized for what I need, and it better be low power because now it's battery optimized, battery powered. But I have a lot of focus and a lot of problems I need to solve on the software side. The number two thing is they're looking for specialized compute, and I talked about that. And lastly, and most importantly, safety, security, and reliability. Those are the three buckets of the industry collaborations that are happening in that space. So let's talk about software. You're talking about over 500 million lines of code. We're looking already at over 1 billion lines of code that they're having to solve for in the market. And that, okay, you say, well, there's a lot of software out there, a lot of industries that use large amounts of software. 1 billion lines of code is, yeah, pushing the limit. But not only do we have to have 1 billion lines of code, we have to do it in a way that's safe and it's secure and it's real time, right? And that's the subtle point. That's why I have to remind people, well, you got a lot of code. Okay, you got a lot of code. Yeah, but we have a lot of code, but I got to make it safe. I got to make it real time. And I got to make it secure. And I got to make it software downloadable, right? Software updatable. And that's really the complexity. It's the combination of those forces that makes it so difficult. And we look at it from 4 different ways. If we're going to solve this problem, we've got to dissect it and address the problem in 4 buckets. One of those is standards. We've got to create reliable standards in the industry that enables us to be able to reuse our software. For once we get it right, we should be able to reuse it. And so we need standard frameworks. At ARM, we're working on a standard framework called SOFI that enables you to reuse your software. But standards across the board, right? Because once you get it right, again, you want to be able to reuse across all your model years. We've got to think about new software methodologies. CI/CD, for example. It's used in the infrastructure place, but can we use it in automotive? It has to if we're going to do real-time software downloads. What about mixed criticality? Workloads sitting together, that one that's a high critical workload, safety workload next to one that's not. How do you isolate those? In ARM, we've made some changes in our architecture that allows for mixed criticality, that allows for confidential compute. That is, that workloads sitting next to each other are confidential to each other. All of these techniques are necessary to have this kind of software in the integration of software that I talked about. Remember I said IVI moving with an ADAS system. When you put those 2 systems together, now you start looking at mixed criticality. Now you're looking at confidential compute and those challenges. And if you're going to have that much software and you're going to download that software in real time, then you have to have a vehicle simulation methodology. Because you're going to have to shift left. There's several problems now. You got to shift left your software development. Your software development has to start before your hardware is available. It's no longer, the hardware is no longer the long pole in the tent. Now it's the software. So you want to shift left. You want to have an environment in which you can start writing software early. That's one. Two, if you're going to download software in real time, you better have some simulation methodologies. You better have a CI/CD technology that allows you to be able to do that in a real-time environment. And that's a vehicle simulation. And of course, we're not going to do this alone. And it is an industry collaboration. There's many areas where we're working collaboratively across the industry. I'll talk about them a bit later. I talked about SOFI. We have over 100 members in SOFI, pretty much all the major OEMs. And all the major OEMs of the world are coming together to work together on this problem because they know the pie only gets bigger as a result of it. It's the idea that, yes, we may be competing, but if we work on these problems together, we will actually make the opportunity for all of us bigger if we solve them consistently, holistically. So the second area, specialized compute. And what do I mean by specialized compute? Well, if you look at this chart, it just kind of simplistically looks at all of the different kind of MCUs that are in the car. So I'm moving out some of the very low-end M-class controllers, starting with an auto MCU, all the way up to an ADAS controller. And they're a combination of ARM processors, hopefully, CPUs, possibly a GPU, possibly an ISP if you get up in the right-hand side, number of CPUs, number of ISPs, number of GPUs, number of central controllers. So again, the variation that's required across all the different systems in a car vary in the number of CPUs, GPUs, ISPs you need, but they're all heterogeneous. And they're all a combination of some level of these, right? It's like puzzle pieces that come together. The level of compute is uniquely different. Not only is the level of compute uniquely different, it's going up rapidly for every one of these. So think about the digital cabinet. I give an example of how many CPUs are in there now and what we're looking at in the future, where number of CPUs are going up 2x in IVI, roughly, 3x or 4x in ADAS and in autonomous applications. So they're dealing with an onset. Not only do I have to solve the problem of heterogeneous compute, now I'm solving the problem of a lot more compute. So not only is it heterogeneous, it's more compute, and the complexity has significantly gone up, as well as the number of memory. Of course, it all scales together. The I/O ring, right? The complexity of this problem has significantly gone up. What happens to that? Of course, your cost goes up. Complexity and cost usually go hand in hand. And so you can see here is 3x more expensive from 7 nanometer to 2 nanometer in costs to do a design. 71% of this is in software verification and IP qualification. So again, what they're dealing with is the complexity has gone up so high, the process nodes are increasing their costs, tape-out costs go up, as well as now I gotta verify and qualify this, which is already a large part of my equation, has just increased as well. And to add to the problem, the number of transistors per chip go up. So all of this is tied together, right? As you add the complexity, as you add more CPUs, the number of transistors, the density of these transistors go up. So that only adds to the compute complexity at these lower process nodes. As well as AI. When you add AI acceleration into the equation, you now have increased the complexity as well, because you're now talking about software defined, you're talking about software, machines writing software. So what does this all mean? Oh, went the wrong way. Got to think about this problem differently. And that's what I mentioned earlier, and I teased the fact that we've got to think about chiplets in the space of automotive. And I've said I've been in automotive for quite some time. You know, we've kind of gone monolithic, right? Because chiplets makes the problem complex. Think about power, think about reliability, think about quality, having a package that's automotive qual that's big enough that can handle a bunch of chiplets at these level compute. Don't get me wrong, the complexity of that part of it is high. We got to solve the problem. We do, because what I just described is a very it's almost the complexity of these solutions are so high that the only way to really be successful, not only from a software standpoint, but from a hardware standpoint, is to dissect the problem. We all know this as engineers. When the problem gets too big, you dissect it, right? You put it into pieces, so those pieces are manageable. And so what we're looking at is, we often like to say what's old is new. Often what we thought about at a motherboard level, we're now looking at a substrate level. We're looking at what the motherboard looked like and putting it all into a substrate. Because your CPUs, your digital IP, is going to scale down to the lower process nodes, right? Process nodes, we know that as process nodes go smaller, digital IP scales really nicely. We like that, right? We get lower, smaller size dies. Whether the cost is less, we don't know. It depends on the IP, the process node. But we do know that the digital IP scales, but we know that memory doesn't. We know that IOs don't. And so it doesn't make sense to put all of this in a 2 nanometer in a silicon when it doesn't scale. It gets very expensive. That's one way to look at it. Another way to look at it is if you put it into pieces, you verify that piece, and you know it works, you qualify that piece, and then you know the software works on that, and then you could put multiple of them down, and that scales your compute, and you start to solve that range question I was mentioning earlier, where it said down to the low end, all the way to the high end, the number of CPUs that are required. You now can just scale it from just tiling CPUs that are already verified, that are already done, they're qualified. We know they work. And your software scales because we know that the same components being repeated. And then you can vary the number of acceleration you need. How many ISPs do you need? Do you need a GPU? Is this an IVI controller? An IVI controller, the graphics display is a lot bigger. So again, breaking the problem down is the only way we're going to solve it. Not only does it break the hardware problem down, but it also breaks the software problem. Because when it breaks the software problem down in such that less CPUs, you can scale down, but your software can be reused. Most of it. You can decide how much of it that you need. And you can see that through. So right now, what these OEMs are doing, and it just, if you just fathom how difficult this is, they have multiple models, and they write bespoke software for each one of those solutions. Can you imagine at 1 billion lines of code for them to be able to maintain that? First of all, their P&L is just going to blow up because their R&D just went out the roof, right? And that's what's happening. That's really what's happening. And so they've got to find a way to streamline this. And they've got to do it between hardware and software. And this is the direction that they are all going at some point. It's not going to happen tomorrow, but it is the direction they're all going. And the manufacturing is lining up to help them. And I think earlier, yesterday, we had someone talk about UCIe and the standards that we're working on at UCIe. And that's going to be critical for the chiplet technology and automotive to be successful. So we're a part of UCIe. Intel is as well. I believe AMD is part of UCIe. I hope I said that right. If I didn't, someone can trip me on the way out. I did. Thank you. AMD is part of UCIe. Good. I did it right. Intel and ARM, those are the big brands. And that's important for us. And I know the OEMs are leaning in on UCIe. And watching it very, very closely and participating in it because it's important. Again, they all know this is the only way to go. This is the only way we're going to solve this problem. So then, safe, secure, and reliable. And this is the right room to be talking about that. But that is by far the most important part of this equation. And at ARM, it's something we believe very, very it's a fundamental belief that safety is not an afterthought, that we've got to think about safety certified, safety and IP from the very beginning. It's not something that we can do. And often, what's happened in the past, a little bit about the change. We would make a mobile IP, right? And our history is mobile. So we'd make a mobile IP. In automotive, I was at TI when this was on. We created Da Vinci. We would take the mobile IP and we would put it into a solution that had a bunch of IP that addressed automotive, and then we'd automotive certify it, right? But in order to do that, we had to do a lot of reverse engineering because we didn't have the STLs and everything we needed on the ARM IP or some of the other components. So we were doing reverse engineering, and the amount of time it took us and money it cost us to get it automotive certified was very high. And so what we do now is, because of we see these the momentum in automotive, we actually give all that with our IP. So we call it all automotive enhanced. And it's pre-certified, so it can hit ASLB and ASLD. And that makes life a lot easier for the industry, and also creates rapid time to market for these industry players. So functional safety is how we look at this, and it's so important. Again, the angle we come out of this is safety, functional safety. And we're doing all the work that's needed for functional safety certifications. In addition to that, it's just, again, I said 60 to 70% of ARM's IP, R&D is spent on test and verification. So it's critical that all of the IP that we have in AE is reliable, and it just works off the bat. And this is a list of all the recent certifications we've had for our IP and automotive, ASLB and ASLD. So again, we do this across all the IP. We get certified, we get pre-certified, and this has made functional safety just how we build IP and not an afterthought for our IP, and that's made the industry move a lot faster. The other area that go hand in hand with functional safety is security. So there's functional safety, and then there's security and cybersecurity. With the amount of software I just talked about and the footprint that we're talking about of compute, the vulnerability is high from a cybersecurity standpoint. And the risk is so high because we're talking about human lives. In fact, the question I asked earlier, when is level 5 vehicles, when are fully autonomous vehicles going to get on the road? And I don't know the answer. I don't know the answer because part of that answer is trust. Do you trust putting your children in an autonomous car and letting them off? I don't know. When is that answer? That's fundamentally the question that needs to be answered. And it's not a technology question. It's a human trust question. And trust is built. And so, and then fundamental to that is that we will forgive a human to make a mistake. We will never forgive a robot to make a mistake. So that's just natural human behavior. We just won't. And so this has got to be rock solid. And one of my worst fears is we'll get all the safety right, because functional safety is something we kind of know, we understand. There's all these test libraries, we know how to verify, we know the test coverage on these things. But cybersecurity, someone taking over a car and doing what they want with it, is some scary stuff, what can happen in those environments. And so, again, cybersecurity is fundamental. And we just what we need to do is start with some of the base stuff that we already do. So ARM has system ready, we have trust zone, we have PSA, you've seen those things. We build on top of those, because there's no need to reinvent the wheel. Build on what works. Build on what the industry is already embraced. We add SOFI, that is a framework of software that has functional safety in it. And then we create cybersecurity standards and rules on top of that. But it's a journey together. We are not going to solve this problem alone. There's no one company in the world that can solve this holistically. It will be something that we do through collaboration in the industry. And the way we look at verification and qualification and safety in the company is multitude. It's foundational to everything we do. The process and simulation underpins all of our IP. We have simulation methodologies that we embrace throughout the company. We have a verification process. We have we embrace MBIST and LBIST in our technologies as well. So it's foundational to, again, what ARM does. We amortize the cost of all of this across the entire industry, so it just works. And we've gone one step further with Automotive Enhanced. So to wrap that up, what's most important as we look at this holistically across the stack and I've shown you how we look at that. Safety is first in everything to do, whether it's automotive enhanced or cybersecurity, or just the time we spent on verification inside of ARM and our IP. It is fundamental to making us successful in automotive. And we have to have reliable solutions across workloads. I know one of the things I was talking to a member in this industry, and they said, I could have a car that's fully ASLD certified, but it'll still drive into a wall because the standards themselves haven't kept up with the way the momentum of technology. And that is eye-opening in that it is our responsibility, instead of blindly relying on just the standards that our industry. Of course, they help us, but it's our responsibility to go that step further and ensure that we're creating technology that's safe for the world. And that means that we have to work together to make that possible. And the future of automotive is built on ARM. I hope that was helpful to you. Thank you very much for having me.
I just twisted Dipti's arm to take a few questions.
Drag me back out.
Thanks very much. I think that was really interesting, and I'll get somebody started, but we've got microphones along the sides, so if you've got a question, step up. I'll get you started with one. So this audience in particular is going to be very focused on hardware defects in silicon. As an IP supplier that's depending on other people to do the manufacturing. How do you guys see that role? There's a distributed ecosystem there. What part do you have and what part do your manufacturing partners have?
Well, there is just, it is semi-distributed, right? We verify our IP, and then that IP goes into a process in our manufacturing. So from that standpoint, it is distributed. But that being said, we work very, very closely with the manufacturers. So we know the latest process nodes, we have their libraries, we optimize our solutions on those libraries, and we actually do, surprisingly enough, a lot of test chips so that we run that through, and then we verify that to ensure that it works the way we expected it to work. But again, that's at an IP level. We all know that a true product verification has to be done on the exact product. So now we know that the IP will work in that process, in those process nodes, and we've done the work properly. But remember, often our customers are taking our products and synthesizing them and putting a lot more IP around them, which means they still have to go through a lot of that work as well.
Okay. All right, Stefano, go ahead. Tell everybody who you are first.
I'm Stefano Di Carlo from Politecnico di Torino. I was really interested in the cybersecurity part. You said it's a full stack problem, but everybody's going to be building on your hardware. You mentioned trusted zone and things like that. How scary is it if the foundation is going to be faulty or not secure? The entire customer may fall down.
Yeah,
that's
you're
a
right.
really big responsibility.
And that's why I said it starts with components that we actually already know and know that work and are embraced by the industry. Because we know that there are already foundational components that can be used and PSA certified, whether it's PSA certified, SOFI takes into account all of those as well. And all of these foundational components were done across the industry. So again, they're not something that, whether it's ARM or anyone else is saying this is the answer and it's the only answer. We've worked across the industry. We've come up with it together. And so that's critically important that we get that foundation right, and we have standards for that foundation. And then you got a lot more above that. You got to get it all right, right? That's why it's a full stack problem, because we got to get it all right. But you're exactly right. We do have those answers at the foundation. And honestly, I'll say that the industry is embracing it. We're seeing a lot of progress towards that. So I'm not seeing resistance in the industry. It is actually very open to the solution because it's not the differentiating part. That's not the part that I want to go reinvent as whether I'm an OEM or a software vendor. I just want, please just tell me what to do. I'll just do it. And that's really how the industry has been looking at it. So we have been successful in creating standards on those base levels.
Good. Okay, anybody else? Yeah, go ahead.
Hi, it's Keith with Advantest. I want to hone in on the 60 to 70% that you said is spent in R&D for test and verification. First, thank you very much. We like to hear that. So 2 questions. One is, why is it so high? Is that sort of the norm for ARM, and do you expect that to remain so? And if not, if you're trying to bring that down, you've come to the right place. We're really good at reducing the cost of tests, so.
Yes, I mean, you always want to bring it down, right? I say that almost semi as a brag and semi as a, we'd like to bring it down too, right? And I'll tell you why, it's both. If there's a open source hardware out there that's, you know, I'm not going to say its name. If you guys know what it is, you know what it is. I don't like to name my competition. And there's this belief that you could just do it, that you can just make bespoke IP. And yeah, you can. I'm not saying you can. It can be done. I've been in this industry for a long time. Of course you can do it. But damn straight, you're going to spend the time on test and verification because that's the most important part of that. You can make it. Making it is not the hard part. It's to make sure it works in every use case. That's the hard part, right? And unless you've actually made something in your career, people just think it can be done. It's like, you know, and so it's an eye opener in my way to demonstrate as this stuff. Making something that works is only half the battle. Making something that works all the time and in any environment is the real success. And I'm preaching to the choir, I think here. But so that's one part of that. And remember, we make our IP it has to work across so many different use cases, so many different process nodes. I mean, you asked a question about, you know, we look at a couple of process nodes, we can't possibly do all of them, right? And so there's a lot of thought process that has to go in to make sure that our IP is safe, is reliable and verified in all of these workloads, in all of these different situations, whether it's automotive, mobile, and then the snowflakes that are IoT, right? So that's a very disparate group of things, and so that's part of why this takes so long. But yeah, we're always looking at ways to bring that down, but it does tell you that it's hard.
Okay. Hey, let's thank Dipti again. That was a really inspiring talk.
Thank you.
Thank you very much.